So these are the kind of characteristics you want to get in a good sport airplane configuration. So, you know, a lot of people have been working on this, and usually the approach is to improve conventional airplanes. But, you know, most of the development's been done. We've done things to improve performance with laminar flow. We've reduced weight with composites on some. With the discontinuous leading edge cuff, we've gotten to better stall spin resistance. BRS is, I think, a wonderful invention. You know, Boris Popov is one of my heroes. And, you know, it's only taken us so far. So these safety improvements are definitely good, but they haven't really fundamentally changed the picture. And there have been lots of attempts to reduce the cost of building a conventional airplane. And once again, if you look at things like beaded skins to eliminate ribs, which require a lot of expensive tooling but do work, or, you know, the airplane in the lower right there is the Amy Trojan, which had symmetric airfoil wings with external ribs, so that all four skins were interchangeable, and flat plate tail surfaces to take cost out. But it didn't reduce the cost enough to majorly move the needle, and the cost-performance trade wasn't enough better than the other airplanes that were available to fundamentally change the picture. So, you know, what do we do? Well, first you call Monty Python for your engineering department and say, and now for something completely different. And please understand here that I am in no way impugning Randy Schlitter or the S9. It's a great airplane. But the point here is to completely change the architecture, and the reason I use the S9 is it's got the same engine as the Facetmobile. And the Facetmobile actually, in some respects, will outperform the S9, and it's not inferior in any performance parameter. So that kind of gives you an idea that that configuration is competitive with the conventional wing body tail. So what I'm going to talk about essentially now is some of the reasoning that got me from here to there. You know, it wasn't just pluck it out of midair. And, you know, what are the implications of that technology? You know, standard design approach, and one of the reasons, by the way, the wing body tail configuration has survived for so long, and it's actually a very good configuration, is because the functions are decoupled. The fuselage contains everything. The wing generates lift. The tail creates stabilization and control power. And you can think of each one of these things individually and then stuff a structure in it so it doesn't break, and you've got a quite viable airplane. But if you go to an approach, and you know, in the industry, they have a fancy name for it. They call it multidisciplinary design optimization. But if you basically go into an approach that takes all of these things into account simultaneously, so I'm looking, for example, at the effect of wing configuration on structural weight and things like that, you can sometimes come up with something very different and potentially better. And essentially, that's what I've been doing. So, you know, one of the things I was always fascinated with, even from very early, is the flying wing. I mean, this magnificent thing was, you know, I had that print up on my wall when I was in college. And Jack Northrop articulated it very well. The idea was to come up with a type of airplane in which all of the functions of a satisfactory flying machine were completely contained within the airfoil. In other words, everything on the airplane's working for a living. There's not aerodynamically, there's nothing that's just being dragged along. And, you know, the original YB-49 and later the B-2 proved that he was right in terms of efficiency, in terms of range payload performance. And, you know, you can generalize that to a whole range of configurations where everything lifts. You know, over a wide range of aspect ratios, all the way from the YB-49 down to the X-24. And, you know, in the upper right there, the X-47, which I had the great honor of doing the aero design on. Just to give you an idea of what you can get out of a configuration, that airplane has an aspect ratio of 4 and a max L over D of 19. You know, pretty cool. But, you know, the point is that that basic concept that Jack Northrop articulated of putting everything inside the one envelope doesn't require the airplane to be a high aspect ratio swept wing. However, I mean, by the way, if you look at the citation up here, I highly recommend, if you're interested, to read this paper. In 1947, Jack Northrop gave the Wilbur Wright Lecture to the Royal Aeronautical Society, which is a very prestigious thing to be invited to do. And this paper is brilliant. Some of the things he understood back in 1947, it took the rest of us another 50 years to figure out. But one of the things he says here is the dimensions of the average human body may also be at times the limiting factor. And when you start thinking about it, for building small airplanes, he was right. You know, he notes at the end there, we're building big bombers, we don't worry about it. But, you know, I see how it could be so, right? Well, let's think about that. You know, if you want to take this all-wing concept and apply it to a personal airplane, the problem is that people don't scale. You know, they take a certain amount of height to sit a human and have them be able to see out. And when you get all done, you discover that the minimum chord of a wing that you can get that will enclose, you know, go over a human and back down and close and have enough foot room and enough depth is somewhere in the 17 to 18 feet range. Well, let's look at what happens if we start as with what Jack Northrop did. If I take the plan form of the N9M, which was the 1/3 scale demonstrator for the big flying wing bombers, put the 17.5-foot root chord on there, I end up with an airplane, you know, with a span of 80 feet and 905 square feet of area. Well, that's way too big for a two-seater. So essentially, conceptually, you just start cutting the outer panels off until you get to a reasonable size. And you end up with an aspect ratio of somewhere between 1.5 and 2, and a span of somewhere around 20 to 25 feet. So basically that idea that the people don't scale is what drives the all-wing approach to a low aspect ratio. Well, you know, once again, you learn from the past because people have done an awful lot of interesting experiments. You're really the very first person to think of anything. So, you know, there have been a lot of successful low aspect ratio airplanes done, and some of these were my inspiration for what I did. You know, in the upper left there, there's 555 Alpha, which is the original Dyke Delta, and this year is the 60th anniversary of that airplane first flying. And, you know, I saw a picture of that when I was about 14 years old on the cover of Air Progress, and it's one of the two airplanes that inspired me and warped my view of airplane design forever. And you know, very happy to see that John Dyke was here and got to be interviewed by Charlie Becker and be celebrated for the accomplishment of that airplane. And then there's, you know, you take a look at the Avro Vulcan, which flew one of the longest combat missions in history when it bombed Port Stanley during the Falklands War. And then way back early in history, well, in the 1930s, there were the Arab series with bunch of, and the thing, you know, reading all this history is it's like, these things fly better than conventional wisdom says they should. These airplanes undoubtedly perform well. There's something there, and that's really what got me interested and got me digging into it and eventually led to what I built. And, you know, they're not alone. There's lots of them. David Rowe in Australia has built 3 or 4 of these, what he now calls UFOs, which stands for Useless Flying Object. They actually fly very well. And then, as you can see here, there's a bunch of other history. But the thing that ties all these airplanes together is they all were real airplanes, they all flew, and they all flew quite well and had quite good performance for their power. So, you know, here's all the advantages this approach gives you for a personal airplane. Because it's short and thick, the structure is light. You know, it's in my case with the airplane I built, light tubing structure, simple primary structure, right? I mean, low parts count, of course, you start counting gussets, it's not quite as low as I thought, but still lower than a conventional airplane. Really benign flying qualities. And the neat thing about a low aspect ratio kind of delta-ish airplane is when you go to high angle of attack, it goes into vortex lift, so it won't really stall or spin. And that's a big safety thing. Because the root chord is so large, it has an enormous tolerance for center of gravity travel. The Facetmobile had an allowable center of gravity travel of 14 inches from the aft limit to the forward limit. Why is that? Because the root chord was 18 feet. And when you're thinking percent chord, it really isn't that big, right? And, you know, Lovely occupant protection because you're sitting in the center of this cage and you're a long way from anywhere. So if you have to fly into something, you've got lots of crust space around you. And hugely roomy cabin. In the original Facetmobile, I can sit in the seat and put both hands straight out and not touch anything. If I want to touch the window, I have to actually lean over. And that's nice. Shoulder room is nice. So a lot of reasons to continue. Well, you know, theory is fine. What about practice? So the next thing, once you've got all this theory, is, well, let's do it for real. And this is the FMX4 Facetmobile. Brought it here in October, in 1994. That's, you know, it doesn't get any better than that if you're EAA, you know. I mean, I've dreamed about that cover since I was 15 years old. But yeah, I flew it here in 1994, just to give you a rough idea, from California to here, behind a Rotax 503 46 horsepower engine, I averaged 77 knots. So what were the goals of this thing? Well, the first one is stop talking and start building. You know, you can sketch things all you want. And in some respects, the beginning of actually building the thing happened out here a few years earlier. I was walking along the flight line, and I came upon what I thought was the most god-awful airplane I'd ever seen. It's a little white biplane, and it was a little lumpy, and it was kind of dirty, and it literally had a canopy made of sheets of Lexan held together with sheet metal screws. And I'm standing there thinking all kinds of uncharitable thoughts, and then this little demon whispered in my ear that, yeah, but his airplane is on the flight line at Oshkosh. Where's yours? Yours is a sketch on a quad pad. Get real. So we did. And I'm happy to say that we proved all of the other things on here, including the UFO reports on the way to Oshkosh. I was flying at 1,500 feet over the interstates most of the way. And one of my favorite little UFO stories from the original flight test of the Facetmobile, I was at Chino Airport, orbiting overhead. A friend of mine told me this story because he witnessed it. I couldn't see it. I was in the airplane. And he was following a pickup truck down the airport access road. And the guy was, you know, looking out the window at this thing overhead. And then I turned, and then he turned, and the road didn't. Which, given what's in the ditches out at Chino, could be pretty unpleasant. Okay, I get asked this question a lot. There's your answer. It has nothing to do with the F-117. I didn't even know about the F-117, thank God, at the time, because if I had, given where I work professionally, I wouldn't have been allowed to build this airplane. It's an exercise in simplicity. I probably pay a small amount of aerodynamic efficiency for the facets, but not much, as long as you keep the flow attached. Because the next question people always ask is, doesn't the flow separate? Well, here's the airplane in the wind tunnel. You can see the tufts. The cruise angle of attack, you can see it's completely attached. At 30 degrees angle of attack, if you look very carefully inboard of the fins, you can see the very beginning of a little bit of flow separation. And the interesting thing is, when I was flying the airplane and doing the high angle of attack tests, you could actually hear that happening. The whole inside of the airplane is a big sounding board. And so it sounded like someone was just lightly tapping on the fins. But I could actually hear where the flow separation was happening. So, you know, in 1994, we came to Oshkosh. This picture was taken, you know, a couple of minutes after we got the ropes up. This picture was taken one day later. You know, by the end of the show, we had about a 4-inch deep trench all the way around the airplane from people coming to see it. The other thing that was kind of amusing is we actually wrote on the prop card, this airplane was flown here from California. That did not stop anyone from asking us whether it had flown. I can't blame them. So back then we could still do the flyby pattern. So when this picture was taken, I was out in the flyby pattern showing people that it had actually flown. So what did we actually achieve overall with the airplane? These are the actual measured numbers. It weighed 370 pounds empty on the ramp. That's the zero fuel weight. That included a BRS and full avionics. Now, let me be very precise. That meant my ICOM was handheld was hanging on the clip on the inside of the airplane. But ready to fly, put gas in it, put me in it, 370 pounds. And we flew it as heavy as 740 pounds. So this airplane would carry over 300 pounds of useful load on 46 horsepower. 102 knots at 4,000 feet measured by pacing it with another airplane. And as I've already said, you know, block speed in counting pattern time from Chino, California to here, 77 knots. And if you go full aft stick in flight, it just mushes and sinks at about 1,000 feet a minute. Doesn't depart. Stick still rolls it, rudder still yaw it. So, you know, having completed that experiment, the idea was, okay, what's next? Let's do a two-place. So this concept was the next stage in the journey with something we called FMX5, designed originally in 1995 with the hope of being here at Oshkosh before 2000. Whole lot of life got in the way. And so this airplane never got beyond the RC model and the wind tunnel test, but the results looked really very encouraging. A little bit of the wind tunnel data here. One of the things about this kind of configuration is that you get a very large flat top to the lift curve, and max lift happens at a very high angle of attack. In this test, somewhere around 35 degrees. And since you're approaching at about 12 to 14 degrees angle of attack, you have a huge margin above your approach angle of attack before you hit max lift. And that's very different than a conventional airplane, because a conventional airplane approaches at maybe 10 degrees angle of attack, 10, 12 degrees angle of attack, and stalls at about 15. So you've really only got about 3 to 5 degrees of angle of attack margin. Now the drag gets very high if you hold it back there, so you will mush, but it isn't going to stall, it isn't going to spin, and it isn't going to depart from controlled flight. The other thing about this kind of configuration that's really nice, this is pitching moment on the y-axis, angle of attack on the x-axis, with nose up being upward. And you can see somewhere out around 20, 25 degrees, there's a really strong nose down pitching moment break. So what it means is this thing will self-angle of attack limit very much like a canard will. You just run out of control power. You can't really command it above around 25 degrees angle of attack, which means you can't really command it beyond max lift. And so no matter what you do with the stick, you can't put it in the regime where it would stall or spin. Now, I say can't, but you know, there's this old premise that you can make things full resistant but never idiot proof. This is not a challenge for other pilots to try to see if they actually could. But the point is, the normal kind of control manipulations that would get you into a stall spin in this airplane just get you into a mush. Hello, come on. Okay, which is really important when we get back to the curve of doom. Because what it says is, you know, if I lose the engine in my 150, yeah, if I stall it, I'm still going fast enough to seriously hurt myself. Whereas in the low aspect ratio airplane, I can just mush it into the ground at quite low speed and live through it. Because, you know, the killer in the stall spin usually isn't the speed, it's the impact angle. It's the fact that the airplane ends up going in almost nose first. Now in 2004, we did a study for NASA. In previous years, I've gone through that in some detail in this talk. I'm not going to do that this time. But for those of you who want to get the citation, there it is. And you can also, if you go to facetmobile.com, you can click on and download this entire report. And it actually has a lot of the stuff I'm going to get into shortly in much more mathematical detail than I'm going to subject you to today. Because having demonstrated, yes, it does work, the next question is, why does it work? You know, conventional wisdom says low aspect ratio is inefficient. But the numbers say, well, this airplane does pretty well for the power. So what's going on here? Well, really what's going on here is this. If you step back and look at the airplane at a system level, what's the mission of an airplane? It's to transport payload from A to B. So what I care about is not lift to drag ratio. What I care about is payload to drag ratio. And what that means is, in effect, the lighter the airplane is, the less airplane I'm transporting around, the bigger the percentage of the airplane is payload, the less aerodynamically efficient it can be because it's carrying less, and get away with it. I'm not even going to get into propulsion. The second law of applied aerodynamics to us aero guys is it's always propulsion's fault. You know, the engine is what it is. So if you're thinking from an airframe viewpoint about how to improve efficiency, this is where that multidisciplinary idea comes in, because what you're basically doing is trading structural efficiency against aerodynamic efficiency. And when you go through all the math, the payload to drag ratio turns out to be a lovely simple number. It's simply the lift to drag ratio of the airplane, which is the aero part, multiplied by the payload percentage of the takeoff gross weight, which is the structural part. And the basic idea here is if I do something that hurts it aerodynamically but sheds weight faster, I actually come out ahead if the payload is constant. And once again, this idea is not original to me. I read this paper in a 1965 issue of the Royal Aeronautical Society Journal. This design is actually the ancestor of all of Airbus. This was a design for something that was called the OG Aerobus. It was designed by a gentleman named G.H. Lee at Handley Page Aircraft. And what's interesting is they were looking, if you read his paper, they were looking at a flying wing airliner, and they laid it out, and they were horrified when they got all done to discover it had a much better L over D than all their conventional ones, but it burned just as much fuel to take the passengers. And Lee was smart enough to realize it's because we have all those empty wing panels and we're carrying all that extra weight around. So he just started cutting the tips off. And things got better and better and better. And then he said, okay, well, it looks kind of clunky. Let's blend it a bit. Came up with this configuration. And this paper has a lovely articulation of how saving weight up to a point improves your transport efficiency faster than losing aero efficiency. It's unfortunate this airplane was never built. It got as far as some wind tunnel tests. And the data are out there if you know where to look. Interesting thing is, as soon as you go to higher aspect ratio in a wing body tail, and once again, you get down to first principles. If you take a look at it, and once again, you know, those of you who are pure aero geeks, feel free to do the math. But L over D is dependent only on a few things. Span efficiency, you know, which is why we play with winglets and wingtips and all that kind of fun stuff. Wetted area, the total wetted area, the total skin area that you're dragging through the air, and the skin friction coefficient, which is how much you pay per square foot of skin in terms of skin friction drag. And that's it, pretty much. I mean, you can really screw up a configuration and make it worse than this, but this is almost everything. So once again, let's look at components. One of the things that's interesting about any flying wing airplane, as long as it's blended and doesn't have a fuselage, is you can get a very high span efficiency. So this is a drag polar without the min drag, so it's just the drag due to lift of a it's nice to have an expert joining us. Of the FMX5 from wind tunnel test, without the wingtip fins, without the winglets. And it's got a span efficiency in excess of 0.9. Just to put that in perspective, a typical low-wing airplane is around 0.75. So for the span, you're actually paying less induced drag with a configuration like this than with a conventional airplane usually. And then the other thing that's interesting is because you have these very long chords, you have a very high Reynolds number. And if you look at skin friction drag as a function of Reynolds number, what you discover is at those very long chords, you're actually paying between 18 and 20% less drag per square foot of wing area with the low aspect ratio airplane than with a conventional airplane. So both of these things mitigate the apparent aerodynamic inefficiency of the low aspect ratio airplane. And this is what I just said. So once again, let's go look at data. Well, let's compare two airplanes dear to my heart because I'm a Cessna 150 owner and I love them, and the Facetmobile. And this will illustrate why the multivariate approach really is the way you want to think. Because if I look at simply lift to drag ratio as a function of airspeed, the blue curve is the Cessna, the green curve is the Facetmobile. Well, the aero guy says, well, it sucks. Right? It's worse everywhere. Why would you want to do that? Now I put the payload fraction into the picture and look at transport efficiency. And when we get out to where we actually cruise, the low aspect ratio airplane is actually as good or slightly better. Now, interestingly enough, Facetmobile, because it's a single-seater, is actually even lower than the optimum low aspect ratio because it's only aspect ratio 1. And the sweet spot is between 1.5 and 2, which is where FMX5 was designed as a two-seater. But you know, FMX5 was designed before the light sport rules came out. It was approximately light sport class-ish, but you know, and the NASA study was focused on cost reduction with automated manufacturing and things like that. So, you know, for the light sport rules, it looked like, let's take another pass at it. Let's do something that's LSA compliant, that I can build with my skills, and so this is the airplane that I am now building. FMX7 in my designation list, christened the Bat Ray this year. This is a wind tunnel model at the Cal Poly Pomona Wind Tunnel. And this is the airplane I'm building at home in Independence. I'll tell you a bit more about it as we come along here. Because the light sport rules have the mandated 1320-pound max gross weight. So that makes that payload fraction really important if you want to get enough useful load to be able to fly two full-size people in a reasonable amount of fuel. 1 or 2 seats. Also, interesting, the light sport rules mandate stall speed in cruise configuration, not flaps down. And what that does is force you to a low wing loading. Well, the low aspect ratio airplane already intrinsically has a low wing loading. So you get the stall speed en passant almost as you get the rest of the airplane put together. So one of the steps along the way is we built a 18% 4-foot span RC model. Originally, we flew with those, you can see the twin fin configuration. It flew really well. The inverted V-tail came along later, and I'm going to talk about that a little bit. This thing flew really wonderfully, and one of the very cool things with today's technology is we also had a Pixhawk autopilot in it, and we were able to data log. And I was able to compare the data from the RC model with the data from the wind tunnel, and they correlated shockingly closely. But as an engineer, that's a really cool thing, because if I use one piece of apparatus to measure something one way, and another piece of apparatus to measure the same thing a completely different way, and the numbers match, there's some hint that you might be close to the truth. So it's very, very gratifying to have that happen. Now, I've been working with Cal Poly Pomona for probably 30 years, and some really good young people stepped up and wanted to work on this as a student project. And so they did a bunch of CFD analysis, and I won't share any of the results from that. And then we did 2 wind tunnel entries in the Cal Poly Pomona Wind Tunnel, which is a really nice little wind tunnel. And I'm also happy to say that 2 of the kids who worked on this now work for Northrop Grumman, which is my employer, so we found some very good engineers along the way, too. So here's just to give you an idea, tough pictures of the new configuration with the, you know, it slightly around maybe approach angle of attack or so, and you can see it's just starting to form a little bit of a vortex on the leading edges, otherwise nicely attached flow. But along the way, we tested a bunch of tail configurations. And I kind of was intrigued by the inverted V-tail for 2 reasons. First of all, well, you know, in empennage design, the devil is in the V-tails. I mean, no way around it. But I liked the idea that the 2 tails would brace each other structurally because they join. And then the other trick I can play with that is to bias the rudders outward for pitch trim. You know, some of the Dyke Deltas have a little T-tail on them to help trim so the elevons aren't so far up to trim. I'm going to do this with the rudders on the Bat Ray. So to share a little bit of the data, I have learned something in the years since FMX5. So here's the lift versus angle of attack curve for Bat Ray. And first of all, you can see that the max lift is about 20% better than the FMX5 was. And once again, you can see the flat top lift curve. And we never could stall it because the tunnel support system would only go to 38 degrees angle of attack. And as you can see, we got all the way out to 38 degrees and the lift is still there. And as with FMX5, you got the strong, stable brake at high angle of attack. Now, here, this is for a pretty far forward CG, so we couldn't quite get out to that. But once again, you've got that nice characteristic that as you get near maximum lift, you run out of control power, you can't hold the nose up anymore, and it's self-angle of attack limiting. Now, I'm going to get on to some performance estimates, but I want to make sure you understand what the basis for these estimates are. Everything that I'm about to show you is based in experimental data of some sort. We started with actual weights from the Facet Mobile and scaling and doing increments to get to weights. And I'll talk to the weight numbers in a moment. And then from the aerodynamics, I had a pretty good understanding from the flight test. The Facet Mobile flew about 130 hours in its career about what the drag characteristics of the Facet Mobile were. So I knew pretty much what the minimum drag was, what the skin friction drag was. And then I used the polar shape, the drag due to lift, from the Cal Poly test to build up the full drag polar. Now, the weight is interesting because I tried to do the weight multiple ways. So I did three things. One of the things I did, John Dyke many years ago published a weight breakdown on the JD1 Delta, the earlier version of the Dyke Delta. So I played the game of incrementing down from that and back up with the changes between the Dyke Delta and the Bat Ray. And then I also started with Facet Mobile and said, I'm going to do increments off of Facet Mobile. Heavier engine, little more wing, 2 seats. And the last one was a statistical analysis based on those airplanes I showed you early on. And you get a pretty wide variation. It can tell you that my most optimistic says I can make the empty weight 516 pounds. I don't believe it. If it happens, I will be an extraordinarily happy man. But what's interesting is with fabric covering, the heaviest weight I could make the estimates give me was 649 pounds empty. So I'm designing to 650 empty, and I'm designing to a 1,400 pound max gross to have a little margin above the light sport for the inevitable person who registers an experimental custom built and wants to carry more stuff. So when you look at what that does in terms of the capabilities of the airplane, if you look at useful load, you can see that we're looking at something like 670 pounds of useful load for the Bat Ray, where even one of the best of the certified, and keep in mind the other two airplanes I'm showing here aren't light sport, 2-seaters, is a good bit less than that. And the reason for that, this is where that weight fraction thing really jumps out at you. For these airplanes, that's the Diamond DA-20, which is a composite modern airplane, versus the Bat Ray, and you can see the blue bar is the empty weight and the green bar is the useful load. So if you look at the percentages, you can see how much on the conventional airplane you're spending just to drag the airplane structure around. And on the low aspect ratio airplane, on the Bat Ray, you're got a lot less gross weight. Now that has a lot of interesting characteristics because if you put the same power in the two airplanes, you've got a much higher power to weight on the low aspect ratio airplane, which does wonderful things for takeoff and climb, which I'll show you in a moment. But once again, let's go back to that comparison. If I look at lift to drag ratios again, this is the aero plot, right? Say, well, you know, let's say an aero reviewer is like, well, Barnaby, you beat the 152, but the Diamond's got you beat. Again, your low aspect ratio is everywhere worse than the modern composite airplane. Well, in this case, what I did was I went back and calculated the actual power required to fly as a function of speed. And there you go. What's fascinating is the bat ray and the diamond are lying on top of each other. Because it's so much lighter that even though its L over D is lower, the total thrust required is about the same. And of course, the 152, great airplane, but not the most aerodynamically refined ever done. Now, we go back to the transport efficiency comparison, and here's where it gets really interesting, because now that I've got the L over D of the bat ray up into the optimum for the lower aspect ratio airplanes, because it's got more useful load than the diamond, even though it's taking the same power to fly, it's transporting almost 100 pounds more stuff. Because these are both airplanes flown at max gross. And so if you look here, you can see 15–20% better transport efficiency with the aspect ratio 1.8 bat ray configuration than the diamond. Now here's where the power to weight really pays off. This is rate of climb as a function of altitude. Now, I haven't found a 150 owner yet who's seen 700 feet per minute regularly, but that's what the pilot's operating handbook says. Okay? Diamond climbs better than that. It's got a nice high aspect ratio wing and all that, but look at this. Because rate of climb is a function of excess horsepower divided by weight, even though the bat ray takes the same amount of horsepower to fly a given airspeed, so it has the same amount of excess horsepower, it weighs a lot less. So it climbs better. Now, once again, if I get anywhere near those numbers, I'll be thrilled. If I can really take off, peg 90 knots, and climb 1,600 feet a minute at 90 knots, that's going to be a real fun airplane. The other place where the power to weight and wing loading really pay off is takeoff roll. Because at the high power to weight, it accelerates faster, and with the low wing loading, it takes off slower. So bat ray will break ground in about 400 feet and be over the 50-foot obstacle in about 700 feet, about when the 152 pilot is thinking of rotating. And by the time the diamond rotates, he's gone. He's over 1,000 feet, probably. The low wing loading pays off in approach and landing. What the wind tunnel data tell me is at max gross weight, this airplane will have a minimum speed, not quite a stall, but the full mush, 38 knots. Which means if I put the standard 1.3 VSO to, coming down final, 50 knots down final. There's nothing wrong with coming down final at 60 knots like you would in a 150, but it's that much slower. You land that much shorter, you're that much safer. And now we look, if we compare this to LSAs, which are all on the 13-20 pound, you can see why the Cessna Skycatcher had problems. 486 pounds of useful load is really skosh for doing anything useful. Flight Design actually done remarkably well with the CTLS for a conventional airplane. Hats off to them. But we're still over 100 pounds more useful load with bat ray. So here's the projected performance with the Jabiru 3300. I have to say 120 knots because it's a light sport. But I think it'll actually go probably closer to 130 if I pitch the prop right. But if I pitch the prop down to hold 120 knots, then I'll get even better max rate of climb. But once again, this is all theory. Now let's get real. This is the layout of the actual structure in SolidWorks. This is what we're building. And with that, that's the theoretical part of it. And I want to give you an update on what's happening on various low aspect ratio related projects that I'm involved with. First of all, as some of you probably know, there has been for some years now a replica of the original Facetmobile being built in Independence, Oregon by Bob Engel. And even though various world events have slowed him down, he's getting close. So there's the structure of the replica Facetmobile, and Bob, who is the builder, in the chapter hangar in Independence. They taxied the airplane naked to make sure everything worked. And it's now been covered. It's awaiting paint and a cowling. And then it's time for taxi tests. So it's getting close. In the meantime, in the next bay over, I'm building the bat ray. So one of the things that the guys at 292 pioneered when they started doing the replica Facetmobile is one of our members, a gentleman named Robert Haynes, has a CNC router set up in his garage and also has developed a bunch of software to define gussets and the coping between the tubes automatically. So once you give him the CAD layout, he can cut everything. And all of the tubing and all of the truss in this airplane, and one Bob's building also, was NC cut with the gussets, with the Cleco holes, everything self-jigging, and it all Clecos up just the way it should, untouched, except for maybe a tiny little bit of filing to clean up router, a little galling from the router, which is great. I mean, I'd hate to have to build every one of those tubes by hand like we did with the original airplane. There's one of the outer panels. This one does come apart into 3 sections as compared to the original Fastmobile because at 22-foot span, you couldn't transport it on the road. And I'm actually paying about a 20-pound weight penalty for that when I get done with the attached fittings and twinning up the ribs so that you can take it apart. It's not going to be a folding wing airplane. This is not intended for day-to-day operation. It's more like a manufacturing break. Hopefully, we'll assemble it for flight once, and that'll be it. But if you ever had to take it apart and transport it, you could. So there's both outer panels, fully Clecoed up. And then as of about a week ago, there's the center section. So you can finally see the cabin. The cabin in this thing is 84 inches wide across the shoulders. Because it's from there to there, it's between the floor panels, there's 4 feet. So you're going to have lots of room. I'm not going to sit people way, way out to the sides, but it means if you put 2 people side by side on about 24-inch centers, lots of shoulder room, center stick between the two occupants so that you can share that. But there's lots of room on the sides. You're never cramming yourself in there. Here's another view looking from the back. The tail, the inverted V-tail will mount off of the back of that little delta shape. Pair of tubes right there. And so, kind of in summation, this combination of low aspect ratio, NC building, lightweight, can really do something quite wonderful, I think, for light airplanes. You're going to cruise as well as a conventional airplane. You will probably carry more payload, shorter takeoff and landing, as reasonably immune to stall spin as you can make any real aerodynamic configuration, low landing speed, and all of those things, I think, will build an airplane. It'll be a great personal airplane because it'll be safer, it'll be more useful, it'll operate out of shorter runways, and the fate is kind of also cost at least a little less. And with that, I think it's going to be a great personal airplane. That's why I'm putting in the time and effort to build it. And so with that, that's the end of my prepared material. I'll open it up for questions in a moment. I will point out on the bottom here my website, and it is waynefan.co, not waynefan.com. And also, I have a newsletter where you can, the URL there, you can subscribe, and I send out periodic updates on how things are going. So with that, I'll open it up for questions. Yes, sir. How do we get in it? The question that never goes away. Well, it's actually one of the trickiest things about designing a low aspect ratio airplane. On the Fastmobile, we had a hatch in the floor, and you came in from the bottom. On Bat Ray, I am going to have those floor hatches in, but I'm also going to have, right up in here, I'm going to have smallish, openable window/hatches. And if I could come up with a decent boarding ladder design, it'll be possible to get in and out that way also. But the other thing is, those doors will be for emergency egress if you need it. You know, one of the things I really like about the idea of having a door on the top and a door on the bottom is it doesn't matter whether you're right side up or upside down, you can get out. But it is a big problem because, you know, one of the things you think about, this airplane is so light, if I just put a boarding step under the leading edge and tried to step up, it'd tip over. You know, and you know, if you look at it, the Dyke Delta people have come up with various ways of making ladders and things to get it. But yeah, it's one of the bigger problems. And it's also significant because You know, the whole top of the airplane is part of a lifting wing. So you don't want a real big door or a real big canopy, because if it pops open, you just blew a huge hole in the top of your wing. And that will not do wonders for your flying quality. So still making progress on that. The way we're doing it now is the small hatches on top and the floor hatch on bottom, which will be more than adequate for ship one, and then we'll evolve from there.
Two questions. First of all,
you get one, Ed. Okay, I like you.
If you get slow on approach, can you generate a high sink rate that you can't recover from with power, or it will only be able to recover from power at the high sink rate and get slow on approach? The second question is, what's the ride and turbulence like?
Okay. The first question is essentially the backside of the power curve. If you get slow on approach, will you generate a high sink rate? The answer is, if you really, really tried, you probably could, but you'd have to work at it. In other words, if you just get a bit slow compared to your target, at least this was my experience flying Phasmobile, even 10 knots slow, say, it's like, sink rate's getting a little bit much, let's punch the power and unload a little bit, and no significant altitude loss. And second, ride in turbulence. Yeah, once again, the wing loading is very low, but because a low aspect ratio airplane has a very low lift curve slope, that means that the lift increment per angle of attack is a lot less than a high aspect ratio airplane. That helps mitigate it. So at this wing loading, the ride in turbulence will be roughly equivalent to, say, a 150 or a 172. I would say Phasmobile was roughly like a Cub. The feel is different. Because of the short span, you don't get the roll kicks you sometimes get. So the motion is more heave and yaw. So if you get hit by a side gust, it's very directionally stable. It'll weather vane right away, which was a little disconcerting at first, because you'd be flying along and the nose would just do that. And then once I realized, yeah, it does that, it'll come back in a moment, don't worry about it, it's fine. But in terms of the general G-loading and how badly you're getting beaten up, it's comparable to I would say, other light airplanes. Yes, sir. What about crosswind stability? Actually, a very interesting characteristic of this. You see how it's got this kind of shape, right? So it doesn't make much side force in crosswind. It wants the weather vane. So the best answer I can give you is on the way to Oshkosh in '94, in Phasmobile, which has a wing loading, or we used to call it a thing loading, of 3 pounds per square foot. I landed it in 12 knots dead cross one day. Not that I wanted to, but the next fuel stop was a long ways away, and that's what it was doing. And it turned out that as long as I stayed awake on the rudders, it was fine, because the elevons are really powerful in roll, and the span's short, so keeping that under control was easy. And because of the shape, when the airplane's going sideways, it doesn't make a lot of side force blowing you downwind, but it does want a weather vane. So,
would your inverted V-tail be a little less efficient because of the lever arm versus what you had?
No, the inverted V-tail is actually a little more, because it's actually sitting a little further back. So it'll have a little more rudder power. Way in the back. The standard Stitz aircraft fabric. You know, I'm considering Oratex, but the baseline is just standard classic polyfiber. You know, one of the things in general I'm trying to do here, it's a radical experimental configuration, so I'm trying to use dead standard practice for everything else. One experiment at a time. And you, sir?
I don't know, the balance of your wind tunnel, or is this going to be some sort of quicker?
Oh, no, it's a tractor. No, this is the sting shroud. You know, because, you know, you've got the rigid sting, and then there's a strain gauge balance in the middle of the model. So actually, I had to do some corrections to take the effect of that out of the data. But on this tunnel, there was no way to mount it on a fork mount. Yeah.
You're going to love this. I know you love the facets.
Yes.
Would it perform better if it was nicely fixed?
Would it perform better if it's nicely fared? Well, interestingly enough, by the way, if you look very carefully at the tessellation here, I designed it so it's at least theoretically possible to put battens in there and generate a smooth mobile. My estimate is I'm paying somewhere around 5% in parasite drag, which is about 2 to 3% in total drag for the faceting. I would absolutely love to go do another wind tunnel test with a smooth mobile model and a Phasmobile model and see if I can put some numbers to that. I have not had that opportunity. Yeah.
The
aspect ratio is 1.5 to 2.5. What happens if you get a 1 or fractional aspect ratio?
Well, as you saw with Facetmobile, at 1.0 it works. But what's basically happening is below about 1.5, you're losing L over D faster than you're gaining structural efficiency. So you're starting to get on the wrong side of that curve for overall transport efficiency. You know, at 1.0, as I showed, you know, I got an airplane that's going 100 knots on 46 horsepower with me in it. Works pretty well. Much below that, I think you're probably going to start getting worse fast. Yeah. Yes, sir.
We all know that an airplane will fly if it's a pounds over gross. So, as a designer, what stops you from just adding a few pounds to make your airplane look better than the competition?
Oh, wow. First of all, you shouldn't fly the airplane over gross because the gross weight is there for a reason. That said, yes, most of the time there is reserve. But, you know, just as a general caveat, we put a lot of reserve on airplanes for the day you screw up and don't realize you're doing it. So if you start eating into that reserve consciously, one of these days you're going to stumble over the cliff. But the answer is there is absolutely nothing to prevent me from adding weight to make my airplane look better, except for the fact that I would find that extra weight offensive, and to me it would be uglier because I have sacrificed performance and efficiency for my personal belief, no good reason. You know, I mean, if people want to spend weight for a gorgeous paint job and a gorgeous interior, and it's their airplane and that makes them happy, more power to them. What I'm trying to demonstrate is what this configuration can achieve. How you spend that weightlifting capacity, if you're the customer, is up to you. Let's see, anybody else got a first question before I give this gentleman his second one? Yes, sir. Is my airplane at Oshkosh 22? No. The original Facetmobile is no longer in airworthy condition, and you saw the state of the bat ray as of today. So, I am touching that project every day. So, as soon as I reasonably can, it'll be here. Whether that's next year or the year after, I don't know. Jim? Am I planning to kit this? One step at a time is, I guess, the best way I can answer this. We are doing the work to make sure that what we're doing is repeatable. We're documenting everything. We're making sure the cut files are complete. So even when we find something that doesn't fit quite right, we're not going back in hand fixing it with a file. We're changing the cut file and making a new part. So it will be possible. As to the amount of effort and cost to set up a new business, we'll see where I am in life and what the demand is and all of that. And frankly, if someone else wants to, you know, has the investment and wants to make me an offer, I'll certainly take the meeting. All right, there's somebody over here. Yes, sir. What's the power plant? Right now I'm baselining a Jabbero 3300. But the design was designed with any real airplane engine in the 100 to 125 horsepower class. I think an 0235 would be a little heavy for it. It would work. 0200, it'd also be compatible with some of the Rotaxes. I happen to prefer the direct drive architecture of the Jabbero to the gearbox and all of that. Personal preference. So I will probably put a Jabbero engine on it, but once again, it'll depend on what engine, you know, I mean, if a Creta showed up on my door tomorrow with a, you know, a Rotax IS in it with a here Barnaby, good luck, then it'd have a Rotax IS, you know, or an 0200 or anything else anybody might happen to want to send me. But yeah, that's the baseline for now. But, you know, I've been carrying, you know, and there's lots of room on the front of the firewall. So, you know, that's a decision we'll probably finalize in about 6 months. Yeah, Anthony.
Or was it like a series of cottage industries? Someone could develop a whole wiring harness,
you know, the short answer to that is I don't know. You know, a lot of what this airplane is very compatible with being jobbed out. Because you know, with all the things NC cut, you can job out cutting the gussets to one vendor, cutting the tubes to another vendor. You know, I mean, that whole distributed approach to business works pretty well. I don't know, because I'm not yet planning production. I'm concentrating 100% on getting ship one built and tested. Yeah, I mean, look, the more prefabrication you can do on a kit, whoever built it, the more prefabricated a kit you can deliver to the builder, the less time they spend building it. But that's, for me personally right now, that's a problem for another day. It's a good problem to have someday, but it's not what I'm thinking about right now. Anyone else? Yes, yeah.
I understand the cost constraints.
Sorry, yes.
If you were to use, say, carbon fiber instead of aluminum, yeah.
Okay. There are a lot of different ways you could do it. Just to give you some numbers. The original Facet Mobile, the entire structure, including the, no, not including the main landing gear, but the entire hull weighed 68 pounds, done in 61 aluminum. So how much weight would you save? Now, the one thing, if you can go to something you can bond or weld, is you save the gussets and all of that. So part of what you're seeing here is I designed what I could realistically do with my skills, both as an engineer and as a fabricator. And it is, unless you went to really extreme composite design, the lightest way to do it. That doesn't mean there's not a lot of other approaches that would be valid. And, you know, the NASA study looked at the idea of cutting, using honeycomb core panels and cutting out the facets as individual panels, NC, and taping the whole thing together, which produces essentially an IKEA plane. And it's not a bad idea. I am not the person to design that airplane. So that's part, and it would be heavier than this. It's got a lot of virtue. So I think there's all kinds of fascinating possibilities. But you know, one of the things on any project like this is there's a zillion fascinating possibilities. You have to pick one and go, or you spend your whole time going, well, that would be nice, that would be nice, that would be nice. And pick one, decide that what's going to work, do it, get it flying. Because, you know, once you prove the concept flies and the shape flies, and someone says, hey, I want to build the same shape in a different material, cool, let's go. Yes, sir?
I recall you having some students helping you. Are you doing this up by yourself?
The short answer is both. It's my project. It's a personal project. I'm financing it. I have had the good fortune to have great help from volunteers and friends. In the case of the students, it was because of my association with the university, and it ended up a lovely win-win for everyone because they got to do a very interesting senior project. They got to learn how to do wind tunnel testing professionally. I got a lot of good data, and incidentally, I made sure their resumes ended up on the right desks, and some of them ended up with jobs out of it. So, you know, full points for everyone. The university got to give them this educational experience. I got great data. They learned something. You know, so, and, you know, I have to say, in answer to that question, without Robert Haynes helping me with the, by doing all of this NC work, I would be a year plus behind where I'm at in terms of fabricating it. He's been wonderful. And the whole automated manufacturing stuff that he's doing has been key to this project. It's a little harder to work with them now that I live in Oregon and they're in Pomona, California. So not yet. We'll see. But, you know, it was a wonderful experience to do the two tests. You know, one other thing I'll say about the students is that working with those particular young people really restored my faith in humanity in some respects. You know, we hear all about kids today and all that, but these kids, man, they had the fire. They worked hard. They were interested. And I can see them in their future career. They're going to be great. And that is so cool to get a chance to work with that and maybe make a small contribution to it. So we'll see. I don't know as far as what happens next. Yes, sir.
Different might this be in a pusher?
How much different than might it be in a pusher configuration? At the risk of being snarky, unworkable. Well, consider this. take a propeller of, let's say, 6-foot diameter. Put it just above the trailing edge. Now, put the airplane at 20 degrees angle of attack, which is the tail strike angle. Draw a line forward from the tip of that propeller to the center of gravity, which is, what, 9 or 10 feet ahead of that? Think about how long the landing gear would have to be.
So drastically different.
Yeah, dramatically different, because the real problem is it doesn't integrate with the dam. And so my conclusion very early was to eat the weight, cost, and complexity, because you'd have to put the engine in the center and use an extension shaft, because if you put the engine all the way in the back, it wouldn't balance. So now I've got the engine in the middle, I've got to get the cooling in there, I've got about a 10-foot extension shaft, I've got a real landing gear design problem, and overall in performance, I don't think I gain anything. You may gain some visibility because you're not looking around the engine, but it really doesn't work very well. So, which, believe me, I asked that question. A lot of other people asked that question too. So.
What do I think? How far is Mark coming along on it?
Say again?
How far Mark coming along?
Well, I showed you those few pictures. Yeah, I mean, it's on the gear, it's covered, it needs to get painted. He needs a cowling, and he's doing some minor revisions to the main landing gear. So, you know, a lot depends on how conditions allow, how quickly conditions allow him to work. The airplane's close.
We gave him a ride in one morning,
Yeah,
2 years back.
yeah.
Very, no.
Oh, yeah, he's a lovely man. You know, unfortunately, you know, COVID got in the way of a lot of things for a lot of people. We're coming back, but it has really slowed everything down. I mean, without that, I think he would have probably flown a year and a half ago.
I think it's going to make about half dozen of them.
We'll see what happens, you know. If there's one thing the last 3 years have convinced me is no matter what you think is going to happen, you're wrong. You know, but we persist. All right. Anybody else? Okay, one more, and then. What about the radar cross-section? Let's see. How snarky an answer should I give you? Okay. I have not evaluated the radar cross-section of the airplane. When I was flying the original Facetmobile to Oshkosh, ATC painted me at about 5 miles. What the radar cross-section of that shape could be properly treated, I don't care. I'm not hiding from anyone. So, you know, and beyond that, let's not go there. All right, everyone. Well, thank you so much for your attention. Give me a moment to get my stuff and get out of the way for the next speaker, and I'll be outside if people want to talk a little bit further. Like I said, give me a chance to get done and get out again.